Very good. Okay, I hope you can see, right? Confirm, please. Otherwise, I'm going to. You can see the blackboard.
Yes, Prof.
Okay, thank you. So let me just finish this long equilibrium calculation. Let me just recap 5 seconds. So we have constructed the matrix A, okay? Now what we're trying to do is find the 3, okay, basis vectors of the null space, of the kernel of matrix A, okay? The way we do this is new 1, 2, and 3 are the 3 basis vectors. So A multiplied by any of the 3 basis vectors is equal to 0 by definition. The way we try to find new 1 is by splitting, okay, matrix A into a square matrix of dimension equal to the number of elements. So in this case, 2, hydrogen and oxygen, and a remaining matrix. So you have A1 and A2 multiplying Ni1, which is a vector that we now write in the following way, okay? We have 2 unknown components, and the remaining 3 I'm setting as the canonical basis vectors, so the canonical base. Why do I do this? Well, first of all, let me just multiply A1 by X1, A2 by E1, okay, and I have this system. Well, first of all, now it's a completely determined system of 2 equations and 2 unknowns, which I can find. Now, the reason why I'm alternating, or I'm actually using the canonical base is because now I select, or I select, you see the first species here. Remember that there is an ordering. The first 2 species is always hydrogen and oxygen. Now what I'm doing is I'm progressively selecting each of the other 3 species. So in this case, I'm selecting water, so that I can have a relation, or a stoichiometrically valid relation between hydrogen, oxygen, and water. Okay, so the first position here is occupied by H2O, and the rest I'm just neglecting. Okay, now the second basis vector, so I will now carry out the solution of the second basis vector for k equals 2, okay? I still do something like this. So I don't understand why this thing is not a little bit darker. Okay. Nu 2 is again equal to A1 and A2, which multiplies now essentially X2, okay? And here we have the second canonical basis vector, okay? Like this, okay? So A1 X2 is equal to minus A2 times E2, okay? That's what we are solving now completely. And if we just do exactly the same thing as before, we write down in full, okay, the first matrix 2, 0, 0, 2, that's A1 times the vector, the unknown vector, which is X2 with all the 2 components, 1 and 2. And then on the right-hand side, I have the known, sort of the known terms. So I'm rewriting the matrix A2. And then now, the only difference from the previous case is that I'm selecting the second canonical basis vector. So now, I'm really introducing here the 1, 2, 3, 4th species, which is OH. Okay. And well, this is very easy to solve. I will not solve it for you, but essentially what we find for the second basis vector is the following: minus a half, minus a half. Those are x1 and x2, essentially these two. And then clearly the rest is 0, 1, 0. Okay? So now I'm able to write down the second independent reaction. This was the first one here. Now the second one is very simply 1/2 of hydrogen and 1/2 of oxygen. And this is OH. So you see there is a logic behind all of this. And clearly every basis vector of the kernel of A, by definition, okay, represents a reaction that conserves atoms. Okay. Now, long story short, for K equals 3, okay. Don't let me write this again, but we still have the system. Okay, now we have the X3, first and second component. Then the usual matrix here, A2. And then I have the third canonical basis vectors, okay? And the canonical basis vector with the third component non-zero introduces the final species, which is HO2. So now, if we solve the system, we find something like this. Minus a half, minus 1, 0, 0, 1. Okay, so it's very simply a half H2 plus, so the minus sign, always remember, it's 0 minus a half. Okay, so it's the reactants side, 1 oxygen molecule giving HO2. Okay, fine. So if you remember now, we had to close the system. We had 5 unknowns, remember? The number of moles of equilibrium, so the equilibrium composition, okay? N1, N2, N3, N4, and 5 corresponding to hydrogen, oxygen, water, OH, and HO2, okay? This is what we need to find. And we had written 2 relationships, okay? 2 equations, which represent directly the conservation of atoms. Now what we have to do, we have to take the 3 independent reactions that we just wrote down, okay? And for each of those, write down the remaining 3 relationships that we still are missing. So let's remember that for K equals 1, we had found the independent reaction, which was H2 plus a half O2 giving water. Now for this one, okay, we can write down the condition of equilibrium. The condition of equilibrium meaning, okay, we impose a minimum of Gibbs energy, and the way we do this through this reaction, okay, is by introducing the quotient and the equilibrium constant, okay? So how do we do this? Well, we take the, well, let me just write it here so that you remember, okay? Okay, if you remember, that was the relationship that we have to write. So very fast here, we have to take the pressure, okay, and evaluate for this particular independent reaction the sum of this term. So the term alpha, So for hydrogen is 0 minus 1. For oxygen is 0 minus a half. And for water is 1 minus 0. So it's plus 1, okay? And this product here is simply x1, which is xH2, so the mole fraction of H2, to the power of 0 minus 1. Then for oxygen is 0 minus a half. And for water is 1 minus 0. So it's 1. Okay, and this will be equal at the given temperature will be equal to the equilibrium constant. Okay, we can say that this is the equilibrium constant relative to reaction 1. So we would call it Kp1. Okay, we do the same now for the second reaction. Okay, by the way, remember that we need relationships, okay, in terms of the number of moles. That's what we call our unknowns, okay? So if you want to convert the mole fractions here in number of moles, you just simply write down, well, this is P to the minus a half. And then this would be essentially, well, this would be X H2O divided by XH2 and XO2 to the minus a half, okay? Sorry, plus a half is equal to pressure to the minus a half. So what we do here, we just write down number of moles of H2O divided by the total number of moles. And then again, here is number of moles of H2 divided by the total number of moles, and number of moles of O2 divided by the total number of moles to the power of 1/2. Okay, so what you end up here is something like the total number of moles to the power of 1/2, pressure to the minus 1/2, and then NH2O divided by the NH and divided by NO2 to the 1/2. Okay, and this must be equal to Kp1 at that given temperature. So if you remember, we had written two equations of conservation of atoms. We called them A and B. Those are the two relations. Now we call this third equation C. Okay. And then essentially for K equals 2, okay, you can do exactly the same thing. K equals 2 was 1/2 of hydrogen plus 1/2 of oxygen. Molecular oxygen equals OH. Okay. So in this case, the pressure is to the power of minus a half plus 1. So it's actually, let me write it down in full, minus a half plus 1. So this is 0. So in fact, this is a pressure independent reaction because it conserves the number of moles. The same thing for the total number of moles. Okay, so this is 0. And then we're left essentially with NOH divided by N to the 1/2 and N to the 1/2 of both H2 and O2. Okay. And that's equal to Kp2, which is a constant at this given temperature. Okay, so that would be our fourth equation. And then finally, okay, for the last equation, okay, we have something like this. I will just write it down and then you in full. So that would be, HO2 divided by NH2 to the 1/2 and NO2, okay? And that is Kp3T. So this is our last equation. Okay? Is that clear? Can you see it correctly?
Sí.
Okay, so now remember our unknowns were N1 all the way down to N5, okay? Let's say the equilibrium. And equations are A, B, C, D, and E. So we have 5 equations for 5 unknowns, and let's say the system is solved, okay? Let me just remind you that for each of those equations, okay, expressing the chemical equilibrium, the minimum of Gibbs energy, remember we have a Kp, okay, an equilibrium constant whose definition, remember, was the exponential, okay, of minus delta G0. Now, for each of the 3 reaction, we call it K, and we have a delta G0 K, okay, divided by RT. Remember that the temperature and the pressure are given, okay? And delta G0 for each of those 3 reactions that we have found is the sum on all the species of essentially the usual difference times mu0I. So it's essentially the difference between the standard state chemical potential of the unmixed, okay, reactants and products. Okay, so the system is completely closed. Let me stress and underline the fact that for this course, I expect you to understand and fully know this procedure, okay? Which is not that difficult, okay? I mean, it took us a long time to get here, but really, when you revise this, you should start from the final technique that we just did and try to remember all the steps that we have taken to get to this point, okay? The meaning of delta G0, the mixing Gibbs energy, the fact that there are some reactions that are pressure dependent, and clearly all the way back to the very beginning where we devised conditions of chemical equilibrium as minimum of Gibbs energy, okay, at a certain temperature and pressure that we keep constant. This procedure, which we can call full equilibrium procedure or full chemical equilibrium calculation, was carried out at a given constant temperature and a given constant pressure. Okay? Now, let me just ask another question. Okay? What if the system is a different system, okay? Adiabatic system and not isothermal as it was before. So before it was temperature equals constant and pressure equals constant. Now we're only setting the pressure. But what we're doing to the system is we are isolating the system, okay? So that essentially it becomes adiabatic. So there's no exchange of heat with the surrounding. What do you think will happen? Well, the temperature will clearly change, because before we were essentially forcibly keeping the temperature constant by exchanging heat, okay? Now we're keeping everything inside, okay? We're conserving energy, okay? Inside our system, and we're converting some of the chemical energy into heat, so the temperature obviously will increase, okay? So now, if you think about it, there is an extra unknown, okay? Now, P is still constant.
Yes, Professor.
Yes.
So it is like a constant pressure process where you increase the volume and you maintain the pressure constant.
No, I haven't said anything about the volume, okay?
Okay.
The pressure is kept constant, and obviously you will have to keep it constant by varying the volume, yes, for sure. But the idea here is now on the temperature. So the pressure is still constant, but T now becomes an extra unknown. Is that clear? Okay. So before I was giving you the temperature, okay? And in fact, what were you doing with the temperature? You were calculating this. You were calculating for each of those expressions where you were calculating the equilibrium constants, okay? Now, really, there is an extra unknown. So I need an additional equation for the temperature. Now, what is this temperature? We can call this temperature of equilibrium, okay? And in fact, it has become known as the adiabatic flame temperature, okay? This word flame, you can use it loosely. There is no flame here. But it is indeed, for an adiabatic situation, the temperature that you find downstream of a propagating flame. Of course, we're not dealing with any transport phenomena here. We're not really dealing with the propagation of combustion waves. It's only chemical equilibrium calculation. So it's an adiabatic temperature. Essentially, why adiabatic? Because the system is kept adiabatic. Okay? So in fact, it is a very important concept, because, well, you can't have a super adiabatic system, right? It's just adiabatic. So there's no exchange of heat. You're not adding heat, okay, to the system. So it's really the maximum temperature that your system can express, okay, by virtue of its chemical energy, okay? So whenever you have a conversion of chemical energy into, say, thermal energy, that's the maximum you can have, okay? The adiabatic flame temperature, which, if you calculate it, is absolutely never larger than, say, 3,500 Kelvin in pure oxygen. But generally, more generally, is about 2,000 Kelvin, okay, in air. Okay? So don't come around telling me that we have 5,000 Kelvin of adiabatic flame temperature, because that's never the case, okay? You cannot extract more energy than you have within the chemical bonds of your system, okay? There's no such thing. So every time you have a combustion process, this is what we can rely on, which is good and bad news at the same time. It's clearly good news because we can have a considerably high temperature, okay, and therefore enthalpy sensible enthalpy, okay, that can be used, for example, in a turbine, okay, and to extract some mechanical work. It can also be used in devices such as nozzles, so in sort of gas dynamic devices, where you're converting this sort of thermal energy into kinetic energy, okay? You can do this, for example, isentropically, still adiabatically, and you're converting this through a convergent divergent nozzle. This is what you do, for example, in rockets. What is the bad news? Well, the bad news is that that number there is an upper bound, okay? And sort of you can't go any further than that. You can't go any higher than that, okay? So there is an upper limit really on, let's say well, for a mechanical system, you can really make it bigger, okay? And extract more or less work, okay? But you won't be able to extract more work per unit mass of fuel, okay? That's pretty constant because this temperature is pretty constant. And clearly, the efficiency of your thermal machine is of course, always limited. And in propulsion systems, okay, this upper bound really is an upper bound for the fuel consumption or the efficiency of the system. In rocket engines would be the specific impulse, okay? You can't go any further. And that really ultimately will set an upper bound on things like the velocity increments that you can have from a rocket, okay? Delta V's of the order of, let's say, 10 kilometers per second, but you can extract from I'm giving you actual numbers here just to sort of order of magnitude. It will be more sort of near 10 kilometers per second than it will be anywhere in the order of 100 kilometers per second. So that's why you have interplanetary flight is possible, but the navigation time is of the order of years and not months, okay? And of course, interstellar flight is not possible, okay? And that's because there is an upper bound on the energy you can extract actually from chemical fuels, okay? So we would really need a paradigm shift or some kind of other energy conversion in order to have more efficiency from our devices, okay? So that's very important. Let's go back to what we're saying. So if we have this extra temperature, well, we need essentially another equation. What's the other equation? Well, remember, well, intuitively, it's going to be a conservation of energy, right? Remember that if we go back to the very beginning of the course, the condition of equilibrium for, well, we're talking about here what? A adiabatic system, okay? So ds, okay, for obviously a reversible transformation is a also an isentropic system. And if you remember, for an isentropic system, okay, that is kept at constant pressure and that is impermeable, so there is no change in composition, okay? If you remember, we had this condition here, all right, dH equals 0. So H, and by H I mean enthalpy, remains constant, okay? So the idea here is to couple, okay, the system that we saw before, which is hinged, let's say, on a minimum Gibbs energy, also on a minimum of, or better still, a constancy of enthalpy, okay? So you can view this, if you want, in two steps, okay? Let's say step one is what we saw before, okay? I keep the pressure and temperature constant, okay? And really, this temperature could be any temperature, okay? So let's specify it here, okay? And we apply simply the minimum of Gibbs energy, right? Which is something like this. Oops, the Ni is equal to 0, okay? This is what we did before, making sure that our atoms are always conserved, okay? And we had those 5 equations. Now, and this is a calculation that you can carry out really at any temperature, okay? Provided it's kept constant, okay? There is a step number 2, okay? So these were the 5 equations we saw before. Now, in the step number 2, you still keep P constant, okay? But now you consider an isentropic system, okay? TdS equals 0, okay? So an adiabatic system at a fixed composition. I'm sorry for the handwriting. Composition. So a fixed composition, okay, which is, for example, the one we just saw before. We implemented before, or we found before, and we implement dH equals 0, okay? So dH equals 0 means essentially, because H, remember, is an extensive quantity, so we can write it as HINI. Remember that, again, for the more careful student, this would have to be a partial molar enthalpy, but we proved that the partial molar enthalpy is equal to the specific or the molar enthalpy. So, because there's no mixing enthalpy, remember? And therefore, our equivalent equation, our additional equation is exactly this. Because this has to be constant at every time, we have that the enthalpy at a given current temperature, which is the temperature, where is it? Is the temperature here that we've calculated this thing at. For the current composition that we found in the first step must be equal to, well, the constant, which is essentially the enthalpy of each species at the initial temperature T0, okay, and at the initial composition. So this is essentially the initial state and enthalpy, okay? Okay, so I'm keeping at every time, for every temperature, I'm keeping this enthalpy for any temperature and any composition constant and equal to the initial enthalpy. So I'm conserving essentially energy within my adiabatic system. So they're put very crudely. So that would be my 6th, okay, equation, F, okay, that I have to use in conjunction with A, B, C, D, E, okay? So now the way F is being used is we take this is a nonlinear equation, okay? And we solve it for T. Now this T is essentially the temperature of equilibrium, or the adiabatic flame temperature, okay? That's what it is, okay? So you can see it as a concurrent or iterative process, but in fact, you just take this and you solve it simultaneously with the first 5 equations, okay? And we have a system where now not only do we have the equilibrium composition, but we have also the equilibrium temperature or the adiabatic flame temperature, okay? Most of the computer codes that utilize, that find a chemical equilibrium will utilize a system like this. We'll solve a system of nonlinear equations exactly as the one I specified previously. Remember that H here of any species as a function of temperature is can be expressed as the enthalpy of formation at a given reference temperature plus the sensible enthalpy from the reference temperature to the temperature T of Cp of that particular species as a function of temperature in dT or dt. That's what you have to do. So in the past, I was also illustrating at this point a Mathematica notebook. I think it's a little bit of a waste of time. If you're interested, I can supply to you if you know how to use Mathematica, which is not MATLAB. I essentially end up with a system that is fully analytical, okay, that is being solved now numerically. It's a little long, okay, and complicated, and I think unnecessarily complicated. In terms of algorithmically, I think we should keep it a little bit more simple, because this is one of the, I've noticed during the years, is one of the hard, sort of more complicated things to absorb for a student. Okay, this treatment of the equilibrium of the calculation, the full equilibrium calculation is a little tricky. I will not ask you to solve it numerically clearly, but I will. You're being expected to know the procedure. Okay, how do you proceed given a chemical system? How do you proceed to calculating your equilibrium composition and maybe the adiabatic flame temperature as well? Numerically, what these programs do, some of you may be familiar with a program called CEA, which CE stands for chemical equilibrium. It's a program that has been used for years at NASA. It's doing exactly this. Okay, so that's what's essentially under the hood or behind the curtain. Okay, this is what's happening. You're constructing a system of equations, and you are solving it numerically. Just out of curiosity, the way it is done is all these quantities, for example, Cp, okay, to find H, okay, are usually polynomial functions of the temperature. So numerically, so I'm just talking about what's happening in codes now, in numerical codes. The Cp of a certain species I as a function of temperature, okay, is in fact represented by a function which is some constant r times the sum of a polynomial function of the temperature. So we're counting on L, and L starts from 1 to some number. It could be 3, it could be 5, it could be 7, depending on the accuracy of your polynomial, okay? Let's say it goes up to big L, okay? So really what you have to supply for each species, okay, is essentially these coefficients, okay? So usually computer programs, what they have is they have an an external file that will store for every molecular species, okay, within your system, and there's a bunch of them, it will store these coefficients, A1, A2, A3, these are just numbers, okay? So that now you can plug them in, okay, here, and you can actually have your specific heat at constant pressure for every temperature, okay? And it's pretty let's say accurate, okay? They can be pretty accurate, especially if this L is large, okay? How do you find things like the chemical potential, which is the partial molar Gibbs energy? Well, it's HT, okay, what we just found here. So you take this CP, you plug it into this integral. Okay, these again are constants, okay, which can be stored, for example, in the coefficient, for example, A0 or A1, okay? So that will be HI minus TSI, okay? And this is the partial molar entropy. And in fact, this can be rewritten as HI of temperature minus T of SI0. So that would be essentially your mu I0 plus a mixing contribution, which is the usual, okay? So this is what you have to sort of devise or calculate from your tables, okay? From your constants. And again, there is another technique to find SI0. I can just very briefly tell you. SI0 is you can write it down as an entropy of formation, and then again the integral of CPI divided by T, okay? Between a reference state and a temperature T, okay? And so having essentially this polynomial, okay, you can plug it in here and you can have the function here at any temperature, okay? So that's what computer programs do, okay? So now you know, okay? So it's not a big mysterious thing. I think, let's say, why do we spend more than 10 lessons doing this? Because culturally speaking, I don't want to get to an age where engineers have lost consciousness of what is going on in algorithms, in very simple algorithms, okay? It's like, oh, I have to calculate the chemical equilibrium. What do? Well, you go to a computer program. No, an engineer should know what's happening inside the computer program. Maybe you're not going to be asked to write the computer program, but you need to be aware of what's going on inside it, okay? You're not any user, okay? You're not your average user. You are expected to know much more than the ordinary people. You're an engineer. So you're engineers, and as such, a physicist is the same. You know, you have to know what other people maybe don't have to know, okay? This technique that we have learned is actually rather useful if we want to, for example, understand the generic combustion process of a hydrocarbon. So take what I call a generic hydrocarbon. So we're going to another little topic here. Okay, why are we interested in hydrocarbons? Well, 95% of the energy that is being produced or used today worldwide is still produced from different forms of combustion of hydrocarbons, even renewable hydrocarbons, okay? So things like organic fuels or renewable fuels from organic waste to things like that. Okay, half of Brazil is, or even more than that, is fueled by ethanol, which is produced by organic material. Okay, plants. You're still burning things. Okay, in cars, in industries, and things like that, to convert chemical energy to heat. Okay, and the reason why they're so widespread still is an economic reason. Okay, it's extremely cheap to actually have them. They're liquid, very dense at room temperature. They can be easily transported on airplanes, on cars, on ships, and they can be transported in pipelines. So we created a system in 200 and so years that really allowed for the mass industrialization of the planet. As we know, as combustion researchers, we really now have to put all of our efforts to understand how we can mitigate the negative impact on the planet, which is huge. Okay, potentially very, very dangerous. So we need to understand what the generic hydrocarbon is. We're talking about essentially, we saw the carbon cycle, right? We saw the carbon cycle and we saw how it worked. Okay. Essentially, from a primordial atmosphere, the insurgence of and the appearance of life now essentially fixed most of the carbon and the CO2 and the atmospheric CO2 in organic matter. And this organic matter eventually went and was stored in reservoirs, okay, which essentially were under the earth or in the ocean, and if you leave it at that, okay, the planet essentially is in a stable equilibrium. So the carbon cycle is essentially constant, with reservoirs being constant. Okay, now we're burning a lot of this carbon, which is fixed, okay, in molecules, such as, for example, I can call CXHY, okay, and I'm producing, so where X and Y are two numbers, okay, so that's your generic hydrocarbon, and these will, the carbon will be released into the atmosphere in an excess kind of CO2 reservoir, which of course, being a greenhouse gas, is what causes the problem, okay, and we cannot reabsorb it. So how do I generalize the combustion of a hydrocarbon? Okay. Well, we know that we have to start from a chemical system, right, involving this molecule here. So before we start talking about molecules, let's start talking about atoms. So remember, we were counting, or not counting, but in our nomenclature, we were numbering atoms with the index I. So in this case, well, I equals 1, we can talk about the carbon atom. We're burning this in the atmosphere, so we're going to use oxygen atoms as well. 3, well, the hydrogen atom in the hydrocarbon. And we can also add a 4th atom, which is the nitrogen atom, because the nitrogen atom is obviously contained in the atmosphere, although for combustion's sake, it can be considered an inert, okay? So the number of elemental species in this case is 4, okay? Now remember that now for a generic chemical system containing this, we have a minimum set of molecules that we can that we have to consider. Okay, so we count them with the index J here. We start from 1, so clearly our first would be our generic hydrocarbon, CXHY. Okay, we consider molecular oxygen, okay, as a second species. The third species could be molecular nitrogen. So these two in a special sort of a special composition mixture is actually your atmospheric air. And then the two main products, which are CO2 and water, okay, H2O. Okay, this is the minimum set. Okay, I have to add essentially the reactants and the products. I could add some intermediate species and have it as big as you want. Okay, but I'll leave it at that just to keep things simple. And so the number of species is clearly 5. Okay, so we can really now carry out, let's say, a full equilibrium calculation. And the first thing we would have to do here is, well, give you an initial composition, obviously, and write down the 4 equations of conservation of atoms. Okay, so we have, so Ne equals 4 equations of conservation of atoms. Okay, so I give you the initial composition. Okay, and we can write down 4 equations, which you can do by yourselves. It's quite straightforward. Okay, what I'm interested in here is really to write down the stoichiometric vectors. Okay, so the independent reactions. How many independent reactions do we have in this particular case? Well, we have NS minus Ne, which is equal to 5 minus 4 is 1 independent reaction. Okay, so we have essentially only one, okay, stoichiometric vector, where A, I haven't written it yet. So this is the kernel. So this is the basis of the kernel of A. So it's one-dimensional. Okay, and and clearly an E1 is in the kernel of A. So let's write matrix A. Okay, composed of the elements A, I, J. Okay, I think you can write it by yourself. So remember, the rows, okay, contain each row, okay, it refers to one of the 4 atoms. So atomic species. So it's carbon, oxygen, hydrogen, and nitrogen, right? And each column is a species. Okay, and we have to count the number of carbon atoms in the species. So this is CXHY. This is O2. This is N2, etc. CO2 and H2O. Okay. So if we do it very, very quickly, this would be X 0, 0, 1, 0. Okay, that's the carbon atoms in each species. The oxygen atom, that would be 0, 2, 0, 2, 1. The hydrogen atom, well, here we have Y atoms in CXHY, and then no hydrogen here, here, and here, and only 1. And then for the nitrogen, it's basically boring because it's 0, 0, 2, 0, 0. Right. So how do we express? How do we find Ni1? Well, we remember we have to split this matrix into matrix A1 and A2 in this way. So we have a 4 by 4 matrix where 4 is the number of elemental species, and we're left with this matrix here, which is a 4 by 1. Okay. And we express our
Yeah, Professor.
harmony. See.
In the third row of fifth column, the hydrogen atom is 2, Professor. It's H2O.
2. Yes, very good. Thank you. So that's 2. So Ni1, how do we express Ni1? Remember, we have, well, it's in the form X and E, right? In this case, E1. But really, X is now 4-dimensional. So we have 4 components here. 1, 2, 3, 4. So we're only left with essentially, how can I call it? A degenerate canonical basis, okay, which is just the scalar 1, okay? Here. Okay? So that now I can write down A1, A2, okay? X and E, so X1 and, well, I'll put it over here, the vector thing, is equal to 0. So I have to solve the system A1, X1 equals minus A2, E1, okay? So let's do it very briefly. So I take A1 as a submatrix here. So it's X 0, 0, 1, 0, 2, 0, 2, Y 0, 0, 0, and 0, 0, 2, 0, okay, which multiplies my 4 unknowns. 1, 2, 3, 4. Okay, and on the left, on the right side, I have this column here, which is 0, 1, 2, 0, which multiplies E1, but E1 is simply the scalar 1. Okay, and now we have to solve essentially for x1, x2, x3, x4. And you can do it by yourselves, okay? Don't invert this matrix. It would be stupidly long. This don't crack, not with a sledgehammer. Just do it by multiplying and by substitution. And in this case, you will have the following, okay? For the first component, we find minus 2. The second one, we have minus a half 4x plus y, 0, 2x, and y. Okay, remember, all of these refer to a species, the hydrocarbon, CXHY, oxygen, nitrogen, CO2, and H2O. So we can now write the only independent reaction that we can write among all these species that conserves the atoms. Okay, it's an automatic procedure. So again, the minus sign means that it's reactants. So 2CXHY, that's the hydrocarbon. 1/2 4x, I don't know why I put a comma here. 4x plus y, moles of H2. And then on the right side, we have, well, we skip nitrogen, okay, for a very good reason. Because nitrogen in this particular case is acts as a dilutant because it does not appear in any of the other molecules, okay? So it doesn't take part in the reaction. So actually this 0 means a very specific thing. It means that, remember what this is, okay? This is, each component of this is, forget that, is Ni double prime minus Ni prime, right? Of the component I. So it's not, it doesn't say that it doesn't appear. It says that it appears on the right and on the left with the same stoichiometric coefficient. That's why it's a dilutant. So we're not going to add it just yet, okay? You can skip it, but you can also add it and nothing happens, okay? It's purely, it's totally allowable, okay, to add a dilutant on the left and on the right, as long as you add it with the same stoichiometric coefficient. But the reaction that do take place, the species that do take part in the reaction is, well, CO2 with the coefficient 2x and y moles of H2O. So you see how easily now we found the generic reaction between oxygen, okay, and the generic hydrocarbon, okay. Actually, you can, for example, divide by 2, okay, and you have something like, plus x plus y divided by 4, O2, okay, and then x CO2 plus y divided by 2 H2O. This is totally equivalent, okay. We just multiplied by a constant, okay. So for example, if x equals 1 and y equals 4, you have methane, okay. So CH4 plus, now you see that x is 1, so this would be 2 O2, okay. X is 1, so we have CO2, and y is 4, so we have 2 H2O, okay. So it's like automatically conserved, but you can do it for any, okay, hydrocarbon, okay. So X could be 10, okay. What's Y? It depends on the hydrocarbon, and we'll classify them later on, but you can have saturated or unsaturated aliphatic hydrocarbons, okay, depending on whether you have double, triple bonds between, or just single bonds between carbon atoms, okay. Carbon atom is a very versatile atom, so it can build also, it can construct all sorts of bonds between between each atom, okay. Let me just, now that we have a little time, let's not stop at this, okay? But let's see what is usually going on, which is not the oxy-combustion, meaning the reaction of a hydrocarbon with pure oxygen, but actually the combustion of a hydrocarbon in atmospheric air. So let's talk a little bit about your atmospheric air, okay? So the composition is, well, air, we know, it's essentially a mixture of oxygen and nitrogen, mostly nitrogen, and traces of other species, such as CO2. In fact, the concentration of CO2 is the big issue, okay? Usually CO2 is measured in parts per million, okay? But let's consider now just the bulk. The bulk is oxygen and nitrogen, and usually the way it's given to you, it's horrendous form, in volume. So what does that mean? So it's 21% in volume of oxygen and 79% volume of nitrogen. So if you take the unit volume, okay, of your atmospheric air, 21% of that volume will be oxygen and 79% of that volume will be nitrogen. Now, remember Avogadro's law. Equal volumes of gas at the same temperature and pressure contain the same number of molecules. So I can write down P V1 is equal to N1, number of moles, or number of molecules, if you wish, RT for one species, and PV2 equals N2 RT for a second species, okay? So in particular, if we take O2 and N2 and we plug in the volumes that we've written here, 21% volume of oxygen and 79% volume of nitrogen, okay? We also have, so let's say V1 divided by V2 is equal to 0.79 divided by 0.21, okay? This ratio here is exactly the ratio of the number of moles of nitrogen and oxygen, okay? Nitrogen is up and oxygen is down. So it's about 3.76. So that means that for every mole of nitrogen, for every 3.76 moles of nitrogen, you have 1 mole of oxygen, okay? So for example, if the total number of moles is essentially 3.76 plus 1, this is the number of moles of nitrogen and oxygen, okay? So 4.76, we can find the mole fraction, okay, of, so the composition in terms of mole fraction of the atmospheric air, which is essentially 3.76 divided by 4.76, okay? And of oxygen is simply 1 over 4.76. Okay? Which of course adds up to the same percentages here, meaning that the mole fraction and the volumetric fraction is an equivalent expression. However, this is not true for the mass fractions, okay? What if I am interested in the ratio of, let's not call them, of the mass of nitrogen to the mass of oxygen? Well, I will have to take the ratio of the number of moles, N2 and NO2, and multiply those by the molecular weight of nitrogen and the molecular weight of oxygen. Remember that the molecular weight is measured in grams per mole, okay? So if you multiply by the number of moles, you have grams. So this would be this ratio here, which is, again, 3.76. And then the molecular weight of nitrogen is 28. And the molecular weight of oxygen is 32. So you see that the ratio of masses, okay, is not the same as the ratio of volume. So it would be 3.29. So in fact, in mass, okay, you have for every 3.29 grams of nitrogen, you have 1 gram of oxygen, okay? So you would have essentially 23.3% of oxygen and 76.7. Okay, you can do the math of nitrogen in mass. So you see it's a little different. You can do exactly the same, but with the mass fraction. And again, it's the same. You have 0.233, and for O2 would be 0.767. Okay, that's the mass fraction. Yeah, I have some. Now, let's go back, okay, to our stoichiometric reaction, okay? So we have 1 mole of your generic hydrocarbon, okay, which reacts with X plus Y divided by 4 moles of oxygen, okay, to give Y divided by 2 moles of H2O and X moles of CO2. Okay? In order to not to clutter the thing, I can call this A, okay? So A is X plus Y divided by 4, okay? So CXHY plus AO2 gives me this. Okay, but we said that nitrogen, okay, can be added to this stoichiometric relation, okay, as long as you add it to the left and to the right, okay, because it's a dilutant, and so it appears with a net stoichiometric coefficient of 0, okay. So let's add nitrogen, but let's add it in exactly the same proportions, okay, that we have in the atmosphere. So we still have 1 mole of your generic hydrocarbon. And then what you have is, well, still A moles of O2. So I'll open the brackets here because I will have to add now, to every 1 mole of O2, I will have to add 3.76 moles of nitrogen, okay? So that's air. And clearly everything is multiplied by A so that it's in stoichiometric proportion with your hydrocarbon, okay? So now I still have that the oxygen and hydrocarbon reaction still produces Y divided by 2 H2O plus X CO2. And then I have to remember to add whatever has not reacted. So it's the dilutant, which is 3.76 times A moles of nitrogen. Okay? So you see you have exactly the same stoichiometric coefficient on the right and on the left. Okay? Now, why did we write this? Well, this is the generic combustion reaction of a hydrocarbon in air. Okay? And it's a stoichiometric reaction in the sense that the full amount, okay, of oxygen and hydrocarbon are consumed to form products. So there is no excess fuel or oxidizer on the right, okay? So we're adding the stoichiometric proportions. And so we define what we call an air to fuel ratio, okay? And we will add stoichiometric to remind ourselves that this is what? This is the ratio of the masses of air and fuel. So CHY, okay? that I'm introducing in this reaction, this stoichiometric reaction, that will fully react to produce water and CO2. Okay? How many, so what's the mass of air that I'm introducing? Well, I have to do the following. I have to write down the number of moles of air, remember air, not oxygen. So it's A moles, and then 1 mole to every 3.76, okay, moles of air. So I have this amount, so it's a mixture of essentially O2 and nitrogen, multiplied now by what? By the mole, the molecular weight of air. Okay? And this is divided by, very simply, 1 mole, okay, of CXHY. So the molecular weight of CXHY. Now, as far as the molecular weight of air goes, if you remember, this is the molecular weight of a mixture. You have to take essentially the sum of all the molecular weights of all the components weighed by the mole fraction. So we calculated the mole fraction of nitrogen and oxygen in air. Okay, it's 1 mole of oxygen every 4.76 moles of the mixture times 32, which is the molecular weight of oxygen, plus 3.76 every 4.76 moles of nitrogen, which is 28. And you get something like 28.84. Okay? It's obviously skewed a lot more to the nitrogen side. And so A, if you remember, is X plus Y divided by 4. This is 4.76. Okay, and the molecular weight of air is, we said, 28.84. Okay, and divided by, well, 1 times the molecular weight of the generic hydrocarbon, right? So how do you do this? Again, you take the molecular weight of carbon and you multiply by the number of carbon atoms. So it's X plus the molecular weight of hydrogen times the hydrogen atoms, which is Y. Okay? Very good. So you see now what we've done. We have calculated for any hydrocarbon, so for any X and Y, the stoichiometric air to fuel mass ratio. So how much air do I need, okay, to completely burn, okay, the generic unit mole of, or unit mass actually of hydrocarbon, okay, which is a very, very important concept, okay. For example, in a rocket, okay, if I want to be very near to a stoichiometric ratio, I want to burn all the oxygen and all the fuel that I'm carrying aboard. Well, I need to know what the ratio is between the mass of, for example, oxygen and the mass of hydrocarbon. In this case, it would be air. So, in fact, it's more, let's say, it's more relative to an aircraft, which is an air-breathing engine. Okay, an aircraft will burn a hydrocarbon in air. Okay. An aeronautical engine does not work near stoichiometric conditions, however. It's burning in excess air. Obviously, it's an air-breathing engine. We'll get to that. But the nice thing is that now for any hydrocarbon, I can really write down this ratio, which is the amount of air in kilograms that you need for every kilogram of fuel. So, for example, let's consider X equals 1 and Y equals 4, that's methane, CH4, right? For methane, you just plug in the numbers. You have that A over F stoichiometric, let's call it ST. You plug in the numbers and you have something like 17.16. Okay? 17.16 kilograms of air for every kilogram of methane. You can do this with any molecule. For example, ethane is C2H6, and you have A over F stoichiometric is 16.01. You can do it for C. So that would be X equals 1 and Y equals 0. And what's C? Well, it's carbon. It's coal, okay? Solid carbon. So that would be A over F stoichiometric is about 11.44, okay? The nice thing about this is that we can now define the so-called equivalence ratio. We call it phi, okay? And, well, you don't necessarily work at this particular ratio in masses. So what you do is you take A over F stoichiometric, okay, and divide it by A over F that you're actually working at. So if you want, this would be F over A divided by F over A stoichiometric. Okay? So say this is the working ratio of your engine, and this is the stoichiometric ratio of your fuel. So in this particular case, if phi is bigger than 1, you see that the amount of, in mass, the amount of fuel with respect to air is bigger than the ratio, okay? Stoichiometric ratio. So you're working with excess fuel. So we say that the mixture is rich, okay? Obviously, if it's equal to 1, the mixture is stoichiometric. And if it's less than 1, is the mixture is so-called lean. So when you say rich and lean, you're actually referring to the fuel, okay? So rich means excess fuel, lean means defective fuel, so excess oxygen, or actually excess air, not oxygen. Okay? Very good. So that's a very, very important concept, especially for engines, okay? You need to know exactly the equivalence ratio, okay? Of your mixture. You know that, well, this is something that you probably know. You could definitely do this with a program like CEA, the Chemical Equilibrium Program, or you could do it with the Mathematica notebook, okay? You take, for example, this particular generic hydrocarbon, okay? And you burn it in air at variable equivalence ratio, okay? And you can do this adiabatically, remember? So we can carry out the reaction adiabatically. So we're not exchanging heat with the surrounding. You could do it at constant pressure adiabatically. So, and you monitor what? You monitor the adiabatic flame temperature. So the temperature of equilibrium, okay? And what you will find is, and you probably totally expect this, is that you have some sort of this kind of behavior where essentially the adiabatic flame temperature peaks, okay, at the equivalence ratio 1. Okay, so when the mixture is totally stoichiometric. Okay, and the reason for the long story short for this is that if you operate at rich conditions over here or at lean conditions, what you're actually doing is you're not burning at stoichiometric conditions, then you're actually adding a dilutant, because if you're working at excess fuel, not all of your fuel will react with the oxygen. So you'll be left with some excess fuel that it's unburned, okay? And that will act as a dilutant, okay, to the system. The same thing will happen at lean conditions, where you have essentially excessive oxygen, which will not react all of it. It will only react in stoichiometric proportions with the fuel to produce the products plus excess oxygen, which heats up and reduces essentially the overall temperature. Now, you can think of this, you can think of the fact that you're not really utilizing all of the chemical energy, for example, but only a part of it. The funny aspect about this is that the implications of this are huge. Think of an aeronautical engine. The aeronautical engine works, okay, essentially with huge excess of air, so maybe in this region here, okay? So very, very lean mixtures, okay? And so it's not only the fact that the equilibrium temperature becomes very low, but you could also have problems of ignition. You can also have problems where your mixture does not ignite. You are outside of the flammability, so-called flammability limits, which is something that has to do not so much with equilibrium, but the propagation of flame speed of a premixed flame. But then again, it is related to this concept. So this really drives all the specific design of a combustion chamber. Okay, because you have to create locally, okay, near the injection region, a local region of stoichiometry where the mixture is really stoichiometric. It produces high temperatures, but overall, then you have sort of dilution air that will essentially keep the overall equivalence ratio low as it is. Okay, and this is also beneficial for the turbine blades, which must not be exposed certainly to adiabatic flame temperatures, otherwise they will just melt. Okay, so that really is a driving factor for the design of your combustion chambers. Let me just add one last thing: hydrocarbons. How are they classified? Just so that we can get our terminology straight, they're divided into two main categories, okay? One are so-called aromatic hydrocarbons, okay? Now, aromatic hydrocarbons are essentially cyclic. What does that mean? It means essentially that they are closed molecules, okay? So you know that carbon comes in chains, okay? It polymerizes in a way, so it can stick to other carbon atoms, and it can actually be potentially very, very long, okay? But you can also have a situation where this chain is closed, it's a closed loop, okay? Benzene is one of those molecules. Polycyclic aromatic hydrocarbons, PAHs, are usually usually these chains tend to stick together, okay, and form macrostructures, which eventually will form things like black smoke or so-called soot. Okay? So this is where all the black stuff that's really ugly comes from hydrocarbons, okay? These closed molecules. The rest of the hydrocarbons are called aliphatic. Hydrocarbons, okay? So they're open chains. Okay? Now, you can have categories here. I'll just be very, very brief. Sorry, they'll steal a minute. You can have essentially saturated molecules. So what does saturated means? Well, when you have essentially a chain of carbon atoms, you're adding the maximum number of hydrogen atoms. In this case, there isn't a single double or triple bond. They're all essentially single bonds, okay? You've opened up all the double bonds, okay, so that you can add the maximum number of hydrogen atoms.